This video covers the problems 4 to 9, which are the short answer type questions. Problem 4 is kind of an essay type question, but very brief, just a couple of sentences on each of these two concepts. So what you essentially need to do is explain or just state in one sentence what that concept means, and one or two sentences on what is its significance, advantage or disadvantage. For small ripple approximation, I would just write this equation. VO of t is basically the DC component plus a VO ripple component at the switching frequency. But small ripple approximation involves saying VO of t is approximately equal to simply VO. So the concept of neglecting the small ripple, which should be the ripple should be small because it's an output voltage and we need to meet stringent specifications. But you just need to write these two equations and then say that the concept of neglecting the ripple and writing VO of t to be equal to VO is called a small ripple approximation, and its significance is that this approximation allows us to do easily the steady state analysis of converters, and in particular, instead of solving second order differential equations, all we have to do is just solve algebraic equations. So be as brief as possible, but just cover the important concepts. For interleaved multiphase converters, I would say the concept is operating multiple converters either in parallel or in series by phase shifting the clock signals from one another by 360 degrees over n, where n is the number of phases or number of modules. That's a concept. And in terms of advantages, you can cite the significant reduction in the ripple due to ripple cancellation and the frequency multiplication. So your three-phase converter would result in 3 times the switching frequency as the effective frequency. Okay, then moving on to problem 5, you are given a converter and need to determine whether valid steady state operation is possible. If not possible, give reasons, and if it is possible, calculate the output voltage. So this looks like a forward converter, except that the reset winding is absent. So without that, it actually violates flex continuity principle, because when the switch was on, current was entering the dot. When switch is turned off, we need a current to enter the dot that is blocked by this diode here. So if you will write, it violates volt-second balance principle. So actually that is not, we also need to go one step further. If it is invalid, we also need to suggest a solution that will make the circuit valid. So I would just go ahead and draw the reset winding that we see in forward converter, and that will make it a valid circuit. So all you have to do is to add another winding in the same core connected through a diode. Okay. And then we need to be careful about the dot polarity. The dot for the reset winding is at the bottom. Okay, so it's basically a forward converter. That's all you have to draw. Okay, that's the solution for this. Since it is invalid as it is, we don't have to calculate the output voltage. Problem 6, unipolar PWM inverter, DC link voltage of 400 volts, power 5 kilowatt at unity power factor, grid voltage 240, L filter with L of 1 millihenry, switching frequency is given. So you need to calculate the THD and the grid current. Since it is a short answer 10-point problem, I also made it easier by asking you to assume that the peak value of VAB which is required in calculating the modulation index, to be same as the grid voltage peak. To be accurate, VAB is we need to calculate that VAB would be V grid plus the drop across the inductance, so J omega L IL. But instead of asking you to calculate all of that, I'm just asking you to assume VAB peak is equal to V grid peak. In practice, it is about 1 or 2% difference. If it is 240 volts RMS, the peak is 240 square root 2, and VAB would be probably about 3 volts above that, but we don't have to consider that. So with this, you can directly calculate the modulation index, because that is needed in that long equation that we derived for TH2. So modulation index is the ratio of the peak of your VAB to the DC voltage VD. Okay. So with our assumption of VAB equal to V grid, so the peak would be 240 volts RMS times square root 2 is the peak voltage, and divided by the DC voltage of 400 volts gives you this amplitude modulation index MA to be 0.8485. Okay. Then we had this long equation for the delta I RMS over a complete line frequency cycle. It's 1 over square root 12 pi. Okay, then TS VD over L, then MA, and the square root of, okay. So once you have the equation, you just need to substitute the value of MA and make sure you don't make any mistake in calculations. Okay, that's the equation, and just okay. So the one thing to remember here is the TS to be used in this equation is the effective period. TS is 1 over F effective, which is twice the switching frequency, or 1 over switching frequency is 20 kilohertz, so 1 over 40k, 40,000 is TS. L is given, it's 1 millihenry, VD is 400 volts, MA is 0.8485, so we have all the required quantities here. So we can calculate delta I RMS, which is 0.5463. Okay. Then THD definition is this delta I RMS divided by the RMS value of the fundamental 6 Hz quantity, delta I1 fundamental quantity RMS. So what is delta I1 fundamental quantity RMS? So this would be the power is 5000. Okay, it's given 5 kilowatt, and the RMS voltage is 240 volts, and it is unity power factor. So the fundamental current is power divided by RMS voltage. So that is 20.83 amperes, and the THD can be now calculated as 0.5463 divided by 20.83. Actually, it's given as a percentage, so times 100 times 100. It's comes out to be 2.62%. That is the final answer for problem 6. Okay, problem 7 is actually an AC to AC converter that we did not study in this course, so this problem is not there for your exam. Instead, we covered several other topics that we did not cover last year. Okay, problem 8 is kind of a design problem, but you don't have to design any component values. Just suggest a most suitable topology to meet these power supply or power conversion specification. So what is given is okay, you have a choice. It can be either an AC source at 120 volts RMS single phase or a DC source at 200 volts DC value, but only one source will be connected at a given time, meaning you can use a switch to connect one or the other, but the output needs to be regulated for either of the two inputs. The output should be the same, and it should be a 400 volts regulated DC voltage. And also, if the input is an AC source, this 120 volts RMS, then the current drawn from that AC source should be sinusoidal and at unity power factor in phase with the voltage. So that immediately suggests that you need a PFC. So let's draw the PFC first. For the AC input, this will be your power converter. Just a standard boost PFC, because we need unity power factor operation. Okay, this gets connected, the AC source gets connected to the diode bridge. Output of that goes to the boost converter. Okay, and you can put a load as well. Okay, so just make sure that these values match. You have 120 volts RMS, so this will give you a peak of 120 times square root 2, which is approximately 170 volts. As long as the required output voltage is higher than this 170, then a boost PFC is a viable solution, and the required output is actually way higher, 400 volts, so it is certainly possible to do that. Then the other part, if the input happens to be a DC source at 200 volts, you could still use the boost converter, because now it's a DC-DC converter, taking it pure DC voltage of 200 volts and delivering an output of 400 volts. That is a boost converter. So we can just make use of the same boost here, right? So this is my other source. I can connect the grounds to be same as this one here. Okay. And this could be switched. And then connected directly to the just after the diode bridge, connected to the boost converter. Okay, so this way, if you want the AC to be delivering the output power, then this switch is opened. Then this just operates as a normal PFC. And if the input source happens to be the DC, then you will switch this on, and then again the boost converter will boost this 200 volts to 400 volts. You don't really need to have a switch here, because the DC voltage is 200 volts, and again it is always higher than the 170 volts peak, meaning the DC voltage source is instantaneously higher than the AC voltage all the time. Therefore, these diodes will be reverse biased, so you will not have any conduction from the DC source into the AC or short circuiting. Nothing will happen. So just one switch on the DC side would be sufficient. Okay, so that's the final answer. All I need is this schematic with this new thing that you need to think and draw. Okay, the final problem, a boost converter based PFC again, with an input voltage 340 sin omega t, 60 hertz, and we need a 400 volts DC output, load current of 5 amperes DC. Okay. What is required is to calculate the duty ratio for the boost converter, and calculate the input current also for the given operating conditions. The D of T for a boost, it is 1 minus input over the output. For us, the input is 340. Now we need to use the absolute value, because after the diode bridge, it is the absolute value anyway. So, okay, divided by the output voltage, which we want it to be 400. So that is the required D. You can even write this as 1 minus 0.85. Absolute value of sine 377t. Then to get the input current, let's calculate the power. P out is also equal to P in. Would be load voltage of 400 volts, load current of 5 or 2 kilowatt. Therefore, input current I in of T would be amplitude I in peak would be 2 times 2000 divided by the peak AC voltage is 340. That's 11.76. So I in of T is 11.76. It's going to be in phase with the voltage, so sine 377t amperes. Okay, that's it, we're done.